here to film a short video about Amphibole. Hopefully this will be shorter than my video about pyroxene. I don't know how I managed to talk about pyroxene for 25 minutes, but there you go. And actually, you guys got lucky. You may have noticed that the pyroxene video cut off very suddenly at the end. I actually talked for another probably good 10 minutes after that, but for some reason the video recording of the screen stopped working, and so you couldn't see any of the things I was talking about, and so I just cut that part of the video. So you got lucky there, but I'll try to keep it somewhat shorter for Amphibole. So covering pyroxene and Amphibole kind of around the same time makes a lot of sense because they're very similar minerals in a lot of ways. So the kind of the colors and some of the habits that you're seeing here in these pictures of Amphibole might look kind of similar to pyroxene. And indeed, I think of kind of the main minerals that you learn in a mineralogy class. Pyroxene and Amphibole are two of the easiest to mistake for one another. They look very similar, and they also show up in very similar types of rocks. So I've got here the general formula for an Amphibole. We've got kind of 3 sites listed here in red that can all change their composition to some degree. So we've got a lot of those solid solutions occurring in Amphibole. So there are a lot of different Amphiboles and a lot of different Amphibole end members depending on what minerals go into those 3 sites. But if you look at the stuff that's staying relatively constant here, we have our silicate group. We have an Si8O22, and you'll see when you look more deeply into silicate structures where that ratio of oxygen to silicon comes from. This is a hydrous element, so we've got some hydroxyl ions here at the end. And then at the beginning, we've kind of got all our various other cations. So the A site, this is going to be a pretty big cubic site, so that's going to be taking in our biggest elements, such as sodium, potassium, calcium. Then we've got 2 generally octahedral sites, an X site and a Z site. So X is going to be taking in the bigger. It's going to be the bigger of the octahedral sites, so it can still take in some sodium and calcium, as well as the things we usually kind of associate with octahedral sites, such as magnesium and iron 2+. Then the Z site can also still take in some sodium, it can take in magnesium and iron 2+, but it can also take in some of our smaller octahedral ions, such as chromium, aluminum, and iron 3+. So lots and lots of different possibilities for Amphibole here. So recall again our principle of parsimony, where we're kind of keeping the structure as simple as possible while having all of these different sites that a lot of different elements can fill into. So Amphibole shows up a lot in igneous rocks, which is the main thing we're talking about this week. It also shows up in metamorphic rocks. So the igneous Amphibole that you will have read about in the reading is hornblende. So again, this looks very complicated here, this formula, but you can see that it's really just one form of this more general formula at the top. So we've got our Si8O22. We can sub in some amount of aluminum for that silicon. We've got magnesium, iron, and aluminum here in this octahedral site. We've got calcium in this octahedral site, and then we have some amount of sodium or calcium, somewhere between 0 and 1 formula unit in this cubic site. And so again, depending on how we're filling in these other sites with charge balancing, we may or may not need kind of all of those sites filled. And in fact, when we get to metamorphic amphiboles that we'll be talking more about later, tremolite and ferroactinolite are going to be the 2 main end members. You can see that just like with olivine, we have a magnesium end member for this amphibole, and we have an iron end member for this amphibole. And interestingly, the way the charge balancing works out on these, that cubic site is actually empty. So there's no A site, there's no sodium or calcium or large cubic site coming in here at the beginning of the formula. So looking here at these pictures of Amphibole, you can start to get a sense somewhat to the physical properties. So the habit and state of aggregation, kind of similar to pyroxenes. If you have a nice crystal of Amphibole, which is pretty rare, you're going to have nice prismatic crystal shapes. If you don't have a nice crystal, you're going to have these kind of bladed masses. And that again is going to result from the cleavage patterns we'll talk about in a second here. So pyroxene is going to tend to be blockier because it has cleavage at 90-degree angles. Our Amphibole is going to be more bladed because it has these very oblique angles of cleavage that kind of squish those crystals down. The colors are also pretty similar to what we see in pyroxenes. So we see pretty black amphiboles. Hornblende especially is going to tend to be very black in color. A lot of the metamorphic amphiboles, the actinolite and tremolite, are going to be more green in color. Luster is generally vitreous. Sometimes you can have some other non-metallic lusters in there, but for the most part, it's pretty vitreous. The cleavage and fracture, that's what's really diagnostic, so what's going to differentiate Amphibole from pyroxene is those two directions of cleavage at 56 degrees and 124 degrees. Sometimes that gets rounded to 120 degrees and 60 degrees. And again, similar to pyroxene, we're looking at a pretty medium hard mineral and an average, slightly high specific gravity, kind of on the higher end of silicates, but nowhere near as dense as any of the metallic minerals that we've looked at. All right, so just to talk a bit about that cleavage. So we've got a schematic of a crystal here showing an A, a B, and a C axis. Amphibole in general is going to be monoclinic. So two of these are not going to be at right angles to one another. But when we look on those A and B surfaces, we see these parallel cleavage traces. So again, these are the sides of our pull and peel Twizzlers. And when we look from the top, so here we're looking down the C axis, we see those two cleavage planes, those two sets of cleavage planes that are going at angles, at oblique angles to one another. So looking for these oblique angles is going to be the best way to distinguish an Amphibole from a pyroxene. Unfortunately, like pyroxene, the cleavage on an Amphibole is often not nearly as perfect as the cleavage that you see on micas or on feldspars. So the example down in the middle left here is actually showing pretty nice cleavage. We can see a very nice shiny face here that the light is reflecting off, so that's going to be one of our cleavage planes. The other one, though probably trickier to see, is kind of hard to tell with the shading, but I'm guessing that this dark face here is another cleavage plane kind of coming out of the board at us here. But more likely what we see in Amphibole is something like this picture on the left, where the thing is pretty massive, it's pretty anhedral, and you have to kind of convince yourself that there are indeed these oblique cleavage planes going on. So this can be very tricky, especially if you're looking at an Amphibole or a pyroxene and you're just seeing these surfaces with the parallel cleavage traces. It's very, very hard to tell the difference between an Amphibole and a pyroxene just from the side view. You really need a nice top view where you can see these patterns. And when we get into petrographic microscopes, we'll see that it's a lot easier to see on a microscope these cleavage angles than it is on actual hand samples. And so again, just like with pyroxene, these cleavage patterns are resulting directly from the crystal structure of the amphibole on the microscopic level. So rather than with pyroxene, where we were looking at a single chain silicate, here we're looking at a double chain silicate. So on the right here, I have an image of what a double chain silicate looks like from the side. So you can imagine, kind of built into this structure, the single chain of the pyroxene here, and then a second single chain here that are connected via these 1, 2, 3, 4 vertices. So we have 2 chains that we're connecting together to form a double chain. If we were looking straight down on this chain, on the end of this pole and peel Twizzler, we would see 4 tetrahedra. So we'd see 1, 2, 3, 4 tetrahedra wide chain when we're looking straight down. And so that's what we're looking at here in these crystal viewer images. So each of these blue sets is a double chain, a single double chain. And we're looking straight down the C-axis, straight down the pole and peel Twizzler on that double chain. And so again, there's a whole bunch of different sites, a whole bunch of different atoms that are going on here. But from Pauling's rules, you know that those silica-oxygen tetrahedra bonds are going to be really strong compared to basically everything else that's going on here. And so in order to see where the cleavage planes are, we're going to want to get rid of all that other stuff and look at the spaces between those silica-oxygen chains. So we can't break the chains, as Fleetwood Mac once said. And remember, we don't want to break. You might be inclined to break along these horizontal lines here, but recall that they actually they have a fair amount of stuff. It's not very strong stuff, but there is a lot of it. Whereas these spaces in between these pyroxene chains are actually completely empty. And so it's going to be easiest to break along these diagonal lines. And again, here our diagonal lines look kind of warped, but if we were to zoom out to the hand sample scale, those would be perfect flat lines with these angles of 56 degrees and 124 degrees between them. So here's a few pictures of Amphibole within igneous rocks, what you might expect to see if you were actually looking at Amphibole in a rock. So these are generally, again, they're going to show up as bladed crystals, and they're going to be within intermediate rocks. So if you've taken Geo 101, those intermediate rocks are going to be kind of medium mafic, medium felsic, so they've got some amount of silica and some amount of iron and magnesium. And so in the upper right, we have a rock called a diorite. It's a relatively coarse-grained igneous rock. The light-colored material is plagioclase and other feldspar, and the dark-colored material is our amphibole. It's pretty hard to tell here. So you can see that we're looking at amphibole and not, say, at pyroxene. In some cases, it will be more or less evident. Underneath it, we have a granite. So this granite has both biotite and amphibole in it. From this picture alone, very hard to tell when you're just looking at a black mineral, whether you're looking at pyroxene or amphibole or biotite. You really need a hand sample to kind of be able to look for those diagnostic cleavage features. These next two examples are andesites. So these are just very fine-grained equivalents of the rock in the upper right here. So this rock is made up of lots of very, very, very small microscopic grains of pyroxene and plagioclase. And so we can't see, amphibole and plagioclase. We can't see the grains themselves because they're so small. But it is that mix of kind of black and white colors that gives the rock this very distinctive gray color. This one here is nice because it also has pretty large grains. We call these phenocrysts, these large crystals of amphibole. You can see just how kind of elongated and bladed these crystals are. So that is very diagnostic of looking at an amphibole. And over here, we have a close-up of a rock, a diorite. So like the rock in the upper right, the white would all be plagioclase, and the black would all be amphibole. And so again, especially on some of these crystals, like this one right here in the middle, or this over here, or these guys, you can really see, again, that bladed texture. So that's really what we're looking for when we're looking at amphibole in igneous rocks. In metamorphic rocks, rather than hornblende, which is a relatively black amphibole, we also get in these tremolite and actinolite amphiboles, which have a much more greenish to white color. So on the right over here, we've got, this is actinolite. The light green color would be talc. The dark green blades are actinolite in the metamorphic rock schist. Down here we have a mass. This rock here is made basically entirely of actinolite, no other minerals. So we have these blades that are kind of fanning out and all intersecting and being intergrown with each other. In the center here, we have a fan-shaped bladed tremolite crystal. So you can see the blades very nicely, how they're truncated here. So that would be kind of the C-axis, and we're looking at the sides of those cleavage traces. This is a fibrous form of asbestos, this is a fibrous form of amphibole, and actually is asbestos, so this is not something you would want to breathe because it can cause lung issues because it has such small, fine, splintery crystals here. But it is actually still an amphibole. It would still have that double chain structure if you got all the way down to the microscopic level. And then finally, you do also see hornblende, our dark black amphibole in metamorphic rocks as well. So here, the black color, these black blades are hornblende. The white minerals, probably some kind of plagioclase. And the red mineral here is garnet. So these are pieces of garnet sticking out of this metamorphic rock. All right, and so again, there's a list of 3D models of amphibole and amphibole-bearing rocks on Sketchfab for you to go check out. I'll show you here just a couple of them, but I encourage you to go investigate them on your own. So this is a very nice example of that bladed texture. You can see the way the blades have all kind of intergrown with one another. There's no clear orientation here, so the blades are all at random orientations. So that means that we are looking, again, if you remember from Geo 101, we're looking at a foliated texture rather than a lineated texture. And look on the side here, see some kind of bigger regions of this amphibole. So amphiboles in general are going to tend to be much kind of more elongated. They're going to have a much bigger ratio of width to length than a pyroxene. So pyroxenes are going to be kind of stubby and blocky. Amphiboles are going to be very elongated. So this I'm showing as an example, just kind of how hard it is to distinguish black minerals from one another in many rock samples. So this is a piece of granite. It's actually very similar looking to the piece of granite that we looked at in the SEM activity. So if I turn it kind of like this, you could imagine you were looking at the square, have your pink potassium feldspar, your white plagioclase feldspar. These dark gray areas are actually quartz. That may be kind of surprising to you at first because you don't think of quartz as being a very dark colored mineral. But because we're looking at it in a rock where the light can't travel all the way through it because it's probably being blocked by some mineral on the other side, it actually takes on a much darker, almost smoky looking color, even if it is not itself actually smoky quartz. But then we have these minerals that really are kind of true black, things like this clump here, or these clumps over here. And in this rock, these are actually a combination of both amphibole and biotite. But even though this is actually one of the nicer pictures on this site, we can zoom in pretty darn far here and start to really see some of the mineral structures. It's still really hard to tell in a lot of cases whether what you're looking at is biotite or amphibole. So can kind of convince myself here, this looks like a flake of biotite to me. And maybe I could convince myself that something over here is more elongated, like an amphibole. But this really is a good example of some of the shortcomings of this technique. There's nothing like seeing the way the light kind of bounces off the sides of the minerals for identifying cleavage planes, and that's really what you have to do to be able to tell biotite apart from amphibole, apart from pyroxene. So even when you have a really, really high resolution image, without holding it in your hand, you're still missing a lot of information. But there is some cool information you can get from something like this, and so just to not end on that kind of downer note, I wanted to show this. This is an igneous rock with dark amphibole grains and lighter feldspar grains. But the cool thing about this sample is that we have very large grains on the inside here, so we have very large amphibole grains. And then on the outside here, we have much smaller amphibole grains. And so again, if you've taken Geo 101 and you remember anything about these igneous textures, you could conclude that maybe this rock actually saw multiple cooling rates. When igneous rocks cool very quickly, they form very small crystals, so maybe that's what was going on over here. When igneous rocks cool slowly, they form larger crystals, and so that's more what we're seeing over here. So I think that's a really nice example of some of the textures that we see in these rocks, and those are the sort of things we'd be talking about more in petrology. So that's it for amphiboles. Thank you for following along. Hopefully I kept this a little bit shorter, and I will talk to you later.